Mark Zibikowski is one of the primary designers and development managers of OS2. In his past 6 years at Microsoft, he's developed some notable codes such as loadable device drivers for DOS 2 and 3. He also designed the DOS 2 device driver interface as well as the OS 2 device driver interface. He's currently one of the developers with primary responsibility for the file system, the device drivers, and the interface between them. Previously, he wrote the original linker, Link version 1.0, and he was responsible for the development of DOS 2, 2.1, 3.0, and 3.1, including the network extensions of 3.1.
My talk is on OS2 device drivers. I'm going to describe how the device drivers fit in with perspective into the OS2 product. We're going to talk about some basic OS2 device driver concepts that are going to be necessary for you to write your device drivers. We're going to talk about the memory structure and file structure of your device drivers, both on disk and in memory. And we'll talk about the control structure and responsibilities of the device drivers once they're loaded in. We can see here that we have a rough calling hierarchy between the device drivers and the various components of the OS2 operating system. We have the application making high-level screen management calls to VIO or to GPI, GPI being the Presentation Manager Graphics Interface. GPI and the VIO calls through the hookable WKS and WVS mechanism, as described in Anthony Short's talk, will be routed to the Windows device drivers. These are responsible for managing the physical screen. In the normal case, without the Presentation Manager, the application makes calls to VIO and KBD. These are routed to the base video subsystem or the base keyboard subsystem, and those interact with OS2 and with the physical screen. My talk is going to deal with the most low-level device drivers, those which are responsible for managing block devices with file systems and character devices at the bottom of this slide. These in general are the disk device drivers, tape device drivers, printers, and COM ports. The device drivers occupy the lowest level of abstraction in the OS hierarchy. At the top we have applications making high-level application object-oriented calls to and from Dynalink Libs and to and from OS2. The Dynalink libraries in turn make API calls to OS2. These calls are at a medium level, are typically file system or IPC based, and in general there is one or more calls made by Dynalink Libs to OS2 for every API call from the application. Going one level further, OS2 decomposes the API calls from the libraries and from the application into logical device calls to the device driver through a mechanism very much akin to OS2's or akin to DOS 3's packet-based exchange. There is, of course, greater than one call to the device driver from OS2 for each API call from the Dynalink Libs or from the application. These calls are at a logical level. There is no concept of underlying geometry or underlying structure to the devices. As an overview, the device drivers provide basic services to the operating system. These services fall into two categories. One is doing reads and writes to the physical devices. These reads and writes are at the level of read logical sectors, read byte streams, write logical sectors, and write byte streams. Another channel for control, which is new to OS2, is that of I/O control, implemented through the DOS dev.ioctl API call. I/O control is a method of specifying how to control a device as opposed to passing data through a data stream. Typically, this has been done in previous operating systems, for example, through serial level protocols by embedding escape sequences. This is not efficient and results in fairly complex device drivers as a result. Through the DOS dev.ioctl API, we can pass unformatted or packets without a format that the OS understands to the device driver to allow an application to control how a device driver functions. One purpose in the device drivers is to isolate the operating system from the hardware. There's a standard packet-based interface which allows the operating system to command functions from the device driver. This isolates the OS and prevents the OS from being concerned with things like DMA and programmed I/O. The operating system doesn't need to be concerned about the underlying implementation of your device driver. Further, the operating system is not concerned with the geometry of disks. Track sectors and heads are the province of the device driver and not the operating system. The operating system also isolates the device driver from applications. The device driver runs at ring 0 and is totally in isolation from applications. The device driver does not have any knowledge of any API request that generates a service request from the operating system. In particular, we want device drivers to have no knowledge and to presume no knowledge of OS2 API calls that generated a particular request. The operating system also isolates the device driver from the internal operating system structures and events. This is, as described in previous talks, there are some device helps which provide well-defined services for the operating service functions. These dev helps will be described later. As a review, the operating system and the device drivers conspire to provide OS2 and application independence. Device driver knows nothing about the operating system structures, knows nothing about the application. The application also knows nothing about the internal operation of the device driver, except through the DOS dev ioctl API call. Basic services that are provided by the device driver are read and write calls and I/O control calls. Now let's talk about some concepts that the device drivers must understand as far as the behavior of the operating system. The operating system operates in several modes. There is an initialization mode, a kernel mode, and a user mode. The initialization mode is when the operating system is running the device driver at initialization time when it is loaded in, just like DOS 3. The device driver is loaded in at ring 3. He runs just like a process. This means that he has full access to the Dynalink facilities of the operating system, and he has a limited access to some of the operating system services. Running at ring 3 at this point, we really would like device drivers to have synchronous hardware initialization. It becomes difficult to coordinate, in our experience, to coordinate a task time ring 3 portion of a device driver with the interrupt time behavior that is usually needed for initialization. We are running at this point at IOPL equals 3, which gives us the ability for the device driver to run at ring 3 and to be able to initialize the hardware through ins and outs. One side effect of running at ring 3 is that the device driver really should not store any long addresses. Once you store a long address, this contains an RPL stamp and a specific selector. Once the device driver is finished initializing, the operating system will remap all the selectors to be ring 0 and likely to have a different selector value, so that any addresses that you store, any long addresses, selector and offset, that you store during initialization are likely to be invalid once your device driver has completed its initialization. User mode is when the device driver is running in the context of a client task. The device driver is running, typically in this case, when he's handling a ROM request from the 3X box. There are several instances in which a device driver needs to understand the requests being made by the 3X box, in particular devices that would like to provide emulation for the 3X box int13 and int10 calls. When running in user mode, you have to be aware that the scheduler may preempt you. You are running totally divorced of the protections of kernel mode, which I'll describe later. Hardware interrupts may occur unless you specifically disable interrupts, but in the case of running in the 3X box, you need not worry about disabling interrupts because you are called in under the guise of a software interrupt, so interrupts will be disabled for you. Running in user mode, you have a limited number of dev helps available. These are described fully in the device driver's writer's guide. Kernel mode occurs when you are running in the kernel or in the device driver as a result of some API call, or in the case of an interrupt. There are two subdivisions here of what I just mentioned, task time versus interrupt time. In task time, you are in the context of the requesting thread. You are entered with a request packet passed in ESBX. You are not preemptible. Not being preemptible has some interesting implications. You must be aware that you should not occupy a CPU loop waiting for an event to become ready, because you are effectively wasting time that can be better spent by the operating system and other processes in the system. Most dev helps are available in kernel mode at task time. These dev helps, again, are listed in the specific section of the device driver's writer's guide. One thing to note is that the kernel will set up a CS and a DS for you to be appropriate to your executing mode. You may be running in either real mode or protect mode, but the CS and DS that are passed to you will be valid for those mode. Further, the SS that you will be passed will bear no relation to your CS or DS, and you should not change your SS. In interrupt time, you'll be running in either real or protect mode. The operating system will first receive the interrupt and then will dispatch it off to the appropriate task. At this point, the DS will be set up for you, the CS will be set up for you. You'll be running in real or protect mode. There is no guarantee that you'll be running in either one. Your code needs to be written so that it is independent of this processor mode. In particular, if you are running in protect mode, it is likely that the LDT, or local descriptor table, will be different too. There is a limited set of dev helps that are available at this point also. The most difficult concept to understand for device drivers is that of bimodal addressing. Bimodal addressing is merely being able to deal with addresses that are in both real and protect mode. In general, real mode addresses are not the same as protect mode addresses. In real mode, segment values are nothing more than offset base registers. In protect mode, selectors are protected objects and bear no relation to the value which is placed into them in terms of physical memory address. This means that segment arithmetic, which was valid under real mode, is wholly inappropriate in protect mode. Device drivers really have no reason to perform segment arithmetic. We provide several dev helps that allow you to map between a protect mode address or real mode address and physical memory. Writing your code so that you are actually segment independent and mode independent results in you having to write small model device drivers. You are limited to 64K of code and 64K of data. There are some tricks that you can play to address higher data, and those will be discussed later. Being only code and data, the kernel will provide you the DS and the CS for any access that you may make of that code and data. We also provide mechanisms for you to access the ROM BIOS. The device driver itself needs to be aware that when he is entered as a result of a ROM BIOS call from the 3X box, that you'll be running in real mode only. Typically, the ROM is not dual mode. Most ROMs have hard-coded segments in there, which of course are not translatable in any easy sense to selectors. Also, the ROM is not dual mode in that it also performs segment arithmetic. You need to be aware of this. Finally, we provide a series of dev helps, or device helps, that give access to kernel services. And let's see now, the set of dev helps that are provided are process and scheduler management, semaphores, request packet management, character queue management, memory management, interrupt vector management, timer services, and monitor services. All of the above will be discussed later, with the exception of monitor services, which was discussed earlier in Anthony Short's talk. Device drivers need to be fully reentrant. The task time portion of a device driver may be reentered multiple times, depending on how the device driver is structured, and the device driver writer needs to be aware that he needs to perform as much reentrant coding as possible. These activations may occur due to a device driver blocking in the task time portion, another task being awakened, and then issuing a similar call to the same device driver. Running in kernel mode, however, you're not preemptible, so you need not worry about preemption causing the reentrancy. Like, you must yield to give up the CPU, or you must block to give up the CPU. To aid you in your reentrant tasks, there is a limited set of semaphore dev helps which are provided, which allow you to protect your data across activations. There are some other multitasking concerns which you should be aware of. First of all, protect mode objects are usually movable. When an address is passed into you at task time, that address is pretty much attached to some physical location. However, if you must block and or address that object at interrupt time, it's pretty clear that since those objects move around, any addressing that you perform at task time will likely change at interrupt time or within the context of another task. We provide some dev helps to lock these addresses down into memory. This prevents the object from moving. However, this has some trade-offs that you must make against swapping. The lock calls allow you to lock things for a short term or for a long term. Typically, short-term blocks are expected to be on the order of 10 to 15 milliseconds, typically the time it takes to service a disk request. Longer-term blocks, those necessary for servicing printer requests or keyboard requests, you are required to use long-term locks for that. Long-term locks have the feature that when you make a long-term lock, the object is moved to one particular end of the allocation arena, preventing some fragmentation. Short-term locks lock the objects in place. This causes fragmentation if you have a large number of objects. Therefore, you must be very careful to use the appropriate long or short-term lock. Addressing objects at interrupt time requires you to address them as with physical addresses. We provide some dev helps that allow you to convert at task time a virtual address, be that a real mode or a protect mode address, into a physical address, a 32-bit address. Clearly, this is only relevant if the object is locked. At interrupt time, we provide dev helps that allow you to convert a physical address back into a virtual address appropriate to the mode that you're running in. Once you are given the address at interrupt time, you indicate to the dev help that the address is to be placed into a particular selector, DS or ES. Once those registers are set up, you must not push or pop them. Otherwise, any mapping that we provide through the dev helps will be lost. In review, we've discussed OS modes: initialization mode, user mode, and kernel mode. Discussed bimodal addressing, writing a device driver such that it is independent of mode, independent of the form of the address, the selector offset or segment offset. Discussed reentrancy. Your device driver task time portion may be reentered multiple times based on its blocking behavior. Access to the ROM. The ROM is not dual mode, and you also need to gate access to the ROM based on 3x box requests. I've listed a series of dev helps that are provided by the kernel to give you access to kernel services. Device driver memory architecture. Device drivers are files that are on disk that are loaded at boot time, very much the way they are under DOS 3. These files are new format exes. They are created simply with the new linker and the language processor of your choice. Being a new model exe, these device drivers have full range to the Dynlink's capabilities of OS2. They dynlink to OS2 services. They can dynlink to other Dynlink library services. There are multiple segments that are allowed in your device driver. Only the first two segments are kept, the data followed by code. Multiple segments are useful when you want to place your initialization data into a separate segment for discarding. There's a special header, very much like DOS 3, in which that the system uses for management. This header should be treated as read-only and the device driver should not modify it either at task time or at interrupt time. Device drivers are loaded into low memory. There is no guarantee made on the ordering of the segments or on any contiguity of the segments. You should write your code to be as independent of these modes as possible. Let's talk about the control architecture in device drivers. In initialization time, device drivers are called to attach itself to a hardware, initialize that hardware, and to recognize that hardware exists. The device drivers, in the process of attaching to hardware, need to attach to various interrupt vectors. Under DOS 3, device drivers wrote directly into the interrupt vector table. Under OS 2, device drivers are not allowed to do that. The operating system manages the access to the interrupt vector table, to the interrupt descriptor table in protect mode, and access to the 8259 programmable interrupt controller. The access to the interrupt hooking mechanisms are done via the dev helps. You request that a particular address be attached to a particular interrupt request line on the 8259. You can also elect to attach an address to a 3x box software interrupt. This allows you to gain access when a 3x box application issues a software interrupt requesting access of the ROM. There are some memory allocation dev helps that are provided also. These are for accessing permanent memory. There are API that are available during initialization that allow you to do DOS alloc-segs, for example, but this memory is allocated to the initialization task and will be freed when the initialization task exits. The dev helps for memory allocation allow you to allocate permanent memory above the 1 megabyte line out of the 3x box arena or below the 1 megabyte line, which consumes space that the 3x boxes may like to use. This memory allocation is very useful for device drivers that need to have large amounts of data. You should trade off the benefits of having this data low versus the cost of having large amounts of low data in terms of gaining access to the 3x, giving access to large amounts of memory to the 3x box. There is a subset of the API which the device drivers are allowed to use during initialization time. These are file read, file write, open create, all the file access calls. There are also some limited IPC calls, semaphores, shared memory, which device drivers can use. Device drivers are requested not to make any process creation or process deletion type calls such as kill process or DOS exec program during the initialization. Device drivers are installed and initialized very much the way they were under DOS 3. Config.sys is opened, the file is read. The device drivers are identified. Each device driver is opened, its segments are allocated in low memory, and they're loaded in the order in which they are in the device. However, again, there's no guarantee as to where these segments are located in low memory or any contiguity that there may be between these segments. The device driver is then expected to recognize what type of hardware it's attached to. If the device is a character device and it has the same name as a previously installed device, the system initialization procedure will go down to the previous device and request it to deinstall before your device is installed. This device is allowed, this previous device is actually allowed to opt whether it will deinstall or whether it will reject deinstallation. If it rejects deinstallation, the subsequently loaded device driver will not be initialized. If it does deinstall, the subsequently loaded device driver will be called with an initialization packet and given the chance to initialize. The device driver is expected to attach to the hardware, recognize that the hardware is appropriate, that it's in a functioning state. If it's not, it can reject its installation. If the hardware is present and it appears to be in a running state, the device driver then can attach to the appropriate interrupt vectors and initialize the hardware as expected. The task time portion of device drivers have several responsibilities. The most important is performing the action requested by the packet and marking the packet as being complete. There are two classes of action the device driver can take in order to service these packets. One is to handle the packet at task time, blocking and running within the device driver using the semaphores, and returning with the packet marked complete with the done bit in the flags field. The other method is to queue the packet for interrupt time service, return from the device driver request call. At this point, the kernel will block the thread because the packet is not marked as being complete. At interrupt time, the device driver can then service the packet, mark it complete, and then use the dev help dev done to request that the thread be restarted. There are two types of action that the device drivers can service. One is that of direct I/O. This is the standard read and write of direct sectors or characters. In general, for direct I/O, the device driver should queue the packet up and service it at interrupt time. Most device drivers, however, will want to queue up the packet. Most device drivers will want to service these packets at interrupt time. We provide a dev helps to queue and dequeue, enqueue, and sort packets based on their logical sector. This allows device drivers to perform some optimal sorting based on seek position. Since it's presumed that most device drivers are going to be interrupt driven, and most device drivers being interrupt driven will have to perform address mapping and locking, the kernel itself will pass all addresses inside direct I/O packets as physical addresses. We will already perform the vert to phys request for you. Further, since we're passing these physical addresses, rather than having every device driver in the world lock these addresses down also, we will lock them for you before your task time portion gets control. So it's pretty important that in the case of direct I/O, the addresses passed in the packet will be physical addresses and will be locked, as opposed to the addresses passed through I/O control packets. For I/O control packets, the format of the kernel packet is not specified. The operating system does not have any knowledge of what the layout of the packet is, where segments are, where addresses are, where data is. As a result, we pass these packets through unmodified to the device driver. This presents several difficulties. First difficulty is that the addresses may not be valid. The application may not be well behaved, may pass an invalid selector. We don't want the operating system to fault inside the device driver. We provide some dev helps to perform address validation on these packets. Also, these addresses, by us not knowing where the addresses begin and end within these packets, we can't phys divert them and we can't lock them down. As a result, the device driver must be aware of the format of the packet, must perform all the validation that it can. Passing these addresses as virtual addresses and as unlocked pieces of memory, we really would like device drivers to perform synchronous I/O control if possible. If you must perform asynchronous I/O, for example, changing a baud rate, waiting until the current characters are output before changing the baud rate, you will have to perform your own vert to phys, and you also have to perform your own locking. Within the task time portion of the device driver, there may be occasions for the device driver to have to perform CPU loops. If you must poll or if you must have CPU loops, there is a dev help which allows you to yield to other runnable tasks. We request that you spend no more than 400 microseconds in your device driver in these CPU loops without calling the dev helps. There's also a requirement that we have that there be a 6 millisecond dispatch latency. In the usual case, the device driver should try to yield within the 400 microsecond time, and also try to return to the operating system from the strategy request within the 6 millisecond dispatch time. The semaphores access that we give to device drivers through the dev helps allow you to manage access to your data structures within your device driver. We provide two types of semaphore control. That of the direct semaphores, which map very directly with the semaphores provided in the API, and with a higher performance proc block and proc run metaphor. The direct semaphores are very simple code. It's very straightforward. However, since they share the same structures and same code that the API does, that they are a little more expensive in terms of time, on the order of 200 or 300 microseconds more expensive. As far as proc block and proc run are concerned, these are the internal kernel primitives that it uses for scheduling. Basically, the underlying metaphor is that you block on a 32-bit ID, and the scheduler will remove you from the run queue until a matching run with a 32-bit ID is issued. This 32-bit ID is generated by the caller to proc block. In most cases, the kernel uses the internal convention of passing an address on which it would like to block, the address of a semaphore. Your device driver is not limited to such a convention. You can use any 32-bit ID you'd like. However, be aware that the proc block, proc run metaphor allows you to have spurious wake-ups, and your code needs to be a little more sensitive to the case where you wake up from a proc block and you must retest the event on which you were waiting. In the case of both semaphores and proc blocks, there is a possible return that you can get from both of these calls, stating that there is one return which states that the event with which you were waiting did occur. There is another return which states that you were interrupted from your proc block. This is in the case where you do a long-term block, for example, when you're waiting for a keystroke, and the task time portion of your device driver is requested to wake up and finish due to a signal being sent. In this case, the device driver is expected to return as soon as is feasible after unwinding through its code. For the interrupt time responsibilities of a device driver, it's expected to service the interrupt in a timely manner and return to the interrupt manager. Typically, the device driver does not know its addressing context. It's not running in the guise of either it may be running as a nested interrupt, it may be running interrupting the kernel, and it may be running interrupting a user at time application. There's an unknown addressing context. The device driver is expected to confirm the interrupt by using the dev help EOI and to enable interrupts soon thereafter. However, please note that when you do this, you are setting yourself up for nested interrupts, and as there is a limited stack for interrupts on OS2, you must be careful in terms of nesting too deeply with your device driver. OS2 also provides a mechanism for sharing interrupts. On the old versions of MS-DOS and on old hardware, there are only 16 interrupt request lines to the programmable interrupt controllers. With the advent of more sophisticated hardware, the 16 interrupt lines is not really enough. This is hardware specific and is dependent upon a particular OEM's adaptation of OS2. In the case of sharing interrupts, the device driver is entered with interrupts off. The device driver is expected to return carry when the interrupt is not for that specific device driver. You're expected to poll effectively to see if the specific interrupt that was generated as a result of your device driver. The EOI, however, is still done by the device driver, and at this point it is expected that the device driver return as quickly as possible from the interrupt. Now, there's some addressing issues that are important for the device driver at interrupt time. The fizz2vert is provided for you so that you can convert the addresses which you've stored at task time into addresses that are usable at interrupt time. In general, you don't have to do fizz2vert for the request packets. These request packets are provided in what's called tiled segment, with a selector offset being relevant and valid in both real and protect mode. Once the device driver has serviced the interrupt and has serviced whatever hardware requirements are necessary for that interrupt, it also may elect to restart task time threads. These are done through the dev help dev done request, which basically marks the packet as being done and resumes the task time component. Semaphores are also available in interrupt time also to release access to objects. However, you must be aware that you should not block at interrupt time, as you'll be blocking the context of some running application, which is not necessarily the one that you're expecting to block. At user time, the device driver gains control through a 3x box software interrupt. The device drivers typically want to do this because they would like to gate access to the ROM, for example, to provide compatible int13 access in the case of copy protection. And there is some sophisticated interaction with protect mode activities that may need to take place. This is most commonly used in the case of, as I pointed out, int13, when a disk device driver would like to wait until all protect mode activities cease before allowing the int13 to go through the ROM in as compatible a fashion as possible. We do have some provisions for non-interrupt driven device drivers. We really would like to have as many device drivers as possible be interrupt driven, but we realize that that is not totally feasible. We allow a pseudo interrupt, a so-called timer, to allow your device driver to infrequently pull your device. This saves us the problem of having device drivers spending a great deal of time polling for an event when there can be some overlapped execution be provided by OS2 for other tasks and other device drivers. These timers are effectively pseudo interrupts which are attached to the scheduler clock, and depending on the particular OEM adaptation of OS2, you may receive these timer interrupts, if you will, on just about on a 30 hertz basis. So for a review, we've discussed all the actions and responsibilities of device drivers for initialization, task time, interrupt time, and user time actions.
For additional information on the topic we just covered, be sure to take a look at the written questions and answers that accompanied this videotape.